Okay, so the first question here is about a simple ideal Rankine cycle, and we have to find out the network and the thermal efficiency, and you have to plot the process on a TS diagram. But the process is already uh, here in the TS diagram. I don't know why they have asked us to do that. Anyway, so this was uh, so the most important thing in these kind of problems is to find out the value of enthalpy. So we are going to find out the enthalpies at the third state. This is the turbine inlet. The fourth state, which is the turbine exhaust. The first state, which is the condenser exhaust, and the second state, which is the boiler inlet. So these four states, if we get the enthalpy on these four states, we can uh, find anything and everything that they ask for. So first of all, H3 can be calculated by the conditions given, 3 megapascal and 350 degrees centigrade. So it's going to be 3115.3, and S3, then entropy at this state is going to be 6.7427, and that you can calculate from the table here. And then this is obvious that the entropy at the third state and the fourth state are going to be equal because of the process being isentropic. So if S3 is equal to S4, S4, which is the fourth state, you can see it's a wet state. Now if it's a wet state, you can calculate the entropy at this state using SF plus X SFG at 75 kilopascals, because 75 kilopascals is the condenser pressure. So again, we are going to refer the table at 75 kilopascals and get the values of SF and SFG. That gets us the value of X, which is the quality of steam, comes out to be 0.8857. Again, so H4 is going to be HF plus XHFG, which again can be calculated and observed from the table. So this is HF and this is HFG, HF, HFG, this is SF and this is SFG. So mm, H4 comes out to be 2402.516. H1, which is saturated liquid at 75 kilopascal, the enthalpy can be calculated again from the table. So can be observed from the table. So it's 384.36 right there, here, 384.36. Again, H2, this formula is equal to H1 plus VF1 into P1 minus P2. So volume of fluid at the state 1 into the pressure difference between first state and the second state. Uh, a point to remember here is that we need to keep the pressures in kilopascals. So 3075. So that gets us H2, and rest the turbine work, what this is supposed to be W net. This is W net. So turbine work minus pump work. So turbine work is going to be H3 minus H4, and pump work is going to be H1 minus H2. And that's how you calculate the net amount of work done. and the amount of heat that we have. uh, See, look at 3 and 2. So boiler is responsible for taking our our system from state 2 to state 3, and that's why the amount of Q in can be calculated by H3 minus H2, which comes out to be 2727.91 kilowatt, and therefore the efficiency is 26%. So this was a very simple problem. Now I'm gonna take you to another problem, which is of an ideal reheat Rankine cycle. And so here we need to we're going to follow the same thing. The enthalpies at all these states is what we are going to focus on. And also uh, we are going to look into the TS diagram. So TS diagram is somewhat like that, and the third state and the fifth state, so this needs to be here. So the third state and the fifth state are at the same temperature. This is what they have already told us in the problem, that uh, the steam is reheated to the inlet temperature of the high pressure turbine. So high pressure turbine, the inlet temperature of the high pressure turbine is T3, and after reheat it is taken to T5. So T3 and T5 are the same, which is I think 600 degrees centigrade. Yeah, 600 degrees centigrade. Now H3 can be calculated from the table. Again, observed from the table simply, it's going to be 3582.3. S3 is going to be 6.6755 kilojoule per kilogram per Kelvin. And there is this thing about X6 that we need to pay attention to. They have mentioned that the amount of moisture should not exceed 10.4%. That means the quality of steam is 1 minus 10.4 upon 100, and that gets us to 0.896. The quality of steam is going to be 0.896. Again, S4 must be equal to S3, and that is because the process is isentropic, and that actually leads us to the value of H4. And but we are gonna get into H4 later. For now, at this point of time, we have H3 with us, we have S3 with us, and we are going to directly jump to H6. H6 can be calculated uh, from the table right here, and at 10 kilopascals, that is the condenser pressure. So um, 10 kilopascals is what we're going to look into, and the enthalpy is going to be HF plus XHFG at 10 kilopascal. So again, these are the enthalpies. So this is HF, this is HFG, and this is SF, and this is SFG. Okay, so H6 comes out to be 2335.76. S6 comes out to be 7.37. Again, following the same formula for S6. Now we should know that S5 and S6 are the same. That is because, again, it's an isentropic turbine. This is an isentropic process. That is why. So now if S6 and S5 are equal, we need to find the temperature or the pressure at which entropy is equal to 7.37, the fifth state. So this is the fifth state, the pressure of which it's still unknown. We don't know how much it is. I have already solved it. That is why I've written 4 megapascals out here. But the pressure at which the reheat is taking place is unknown. And that is what they want us to find here. That is the problem number A here. So the pressure can be found out by knowing that the entropy at that temperature is equal to 7.37. So that you need to look into your table of superheated state at some pressure, which coincidentally or by just looking at the table, observing it, comes out to be close to 4 megapascals. So that is how I get the temperature, 4 megapascals, and the enthalpy at this pressure and temperature is equal to 3674.4 kilojoule per kilogram. Again, this temperature has come from T3 is equal to T5. That is the condition given to us. Again, and why have I looked into a superheated table? That is because the enthalpy. Okay, yes, the entropy at the fourth state must be equal to 6.6755. And where has this come from? This has come from S3, and it is greater than Sg, the enthalpy of gas at 4 megapascals. So that is why the fourth state is a superheated state. It's out of the wet region, it's around here. And again, by interpolation, I get that H4 is going to be 3153. So it is somewhere in between these two quantities. You have to apply interpolation to get the value. So H4 comes out to be 3153. H1 is simple. It's going to be HF at 10 kilopascals. So that you can get H1. You, you can get H1 from that table of 10 kilopascals. And then H2 is going to be again that formula. H2 is equal to H1 plus Vf1 into P2 minus P1, keeping in mind that the pressures are in kilopascals. So that gets you H2. Qn is going to be H3 minus H2 plus H5 minus H4. Why are there two quantities of enthalpies being added here? That is because there's a reheat going on, and from state fourth to state fifth, the steam enters the boiler again, and that is why there's an extra amount of heat added. This is Q in extra. So this you need to add here. So that is why the amount of heat is H3 minus H2, the usual, plus H5 minus H4. This is from the reheat part. And W net is going to be the work by the high pressure turbine, by the low pressure turbine, minus the work by the pump. Work by the pump obviously is going to be H2 minus H1. So that comes out to be 1752.8. This is the net amount of work done, and the efficiency is going to be 44.9. Okay, so these are the answers. The pressure at which reheat occurred was 4 megapascals, and the efficiency is going to be 45, 44.9, and TS diagram I've already drawn here. Pressure being equal to 4 megapascals, I'll say that again. Why is the pressure why is the pressure equal to 4 megapascals? The reason why pressure was equal to 4 megapascals is because I had to look in the table for a pressure at which entropy has this value when the temperature is 600 degrees centigrade. I have to look for a pressure where entropy is equal to 7.37 when the temperature is 600 degrees centigrade, because I know S6, S6 and S5 are same. That is how I approached it. So P5 is going to be 4 megapascals. That's how. So this was the second problem. The third problem is going to be that of a regenerative cycle with closed closed feed water heater. And since there is a closed feed water heater, there's going to be a mixing chamber. Now, a closed feed water heaters, the point is that the steam extracted here is not going to come in contact with the steam which proceeds after extraction. So this is 1 minus y, and this is the amount of steam extracted. These two do not mix here in the closed feed water heater. They are going to mix in the mixing chamber. Uh, the important things to remember about these kind of problems is um, the location of these points, right from fourth, fifth, ninth, and second. So you need to understand that the feed water heater is responsible for bringing y amount of steam from state H7 to H3, and for bringing 1 minus y amount of steam from state number 2 to state number 9. So from here to this thing, y from 7 to 3 mixes with 1 minus y, not actually mixing. There's This is a closed feed water heater, so they are going to come in contact. So H2 and H9 is the enthalpy change from H2 to H9 for 1 minus y amount of heat, amount of steam, and for y amount of steam, the entropy changes from H7 to H3. And the mixing chamber is responsible for for the change in state to number 5 when it takes the 1 minus y amount of steam from state number 9 to state number 5, and y amount of steam from state number 4 to state number 5. So this is mixing chamber, this is feed water heaters. So 1 minus y from the ninth state coming out of the feed water heater gets into the mixing chamber and reaches state 5. Y amount of steam coming, Y amount of water, in fact this is converted into saturated liquid. So Y amount of water after being pumped into the mixing chamber comes down to the state 5, and this is what happens in the mixing chamber. So these are very important for you. So we are going to apply energy balance in these two systems. That is why it was important. Again, H6 can be calculated by the this can be observed from the table, superheater table at 3000 kPa, the turbine inlet, and 350 degrees centigrade, and S6 obviously from the same table, and S7 and S6 and S8 are all going to be equal because it's it's an asymptotic process right from 6 to 7 to 8. So that's why that gets you the value of H7, which comes out to be 2852.16. Why have I chosen H7. Why is H7 equal to this much? This is from the um, table of 1000 kilopascals of pressure, and when the enthalpy is equal to 6.7427. So you have to apply interpolation again. So when enthalpy is equal to 6.7427, you have to use interpolation to get the value of enthalpy at this pressure, So H7 comes from there. S8 is going to be a wet state, that is SF plus XSFG, and mm, SF. Now this all is going to be from the um, table again, and at condenser pressure. So it comes out to be, the value of X comes out to be 0.835. Okay. Now H8 can be calculated using this formula. So this comes out to be triple to 1.17. Okay. Now this is interpolation 2852.16. So I think this is a little inexact, and I have no choice but to accept this value, 2852.16. This is the only value I'm not actually that sure about, and that is why there is a slight difference in the value of uh, work produced by the turbine that I have calculated. It came out to be 770, and it is actually 741. Rest everything is same. Uh, this may be the value again. That is because of the interpolation, and rest enthalpy and everything you have to calculate by yourself. H1 equals to HF at 20 kilopascals, and that is true. So you have H1 that is here, so it's supposed to be HF at 20 kilopascals. Again, H2 is going to be H1 plus Vf into P2 minus P1. Just know that the pump is responsible to take, the pump one is actually taking the system from first state to second state, and the second state is that of the, see, second state has the pressure equal to that of the boiler. So that is what you need to understand. So that is why there's a jump from first state to second state. Second state is a state on the pressure line of the boiler. Okay. So again, h1 minus h2, okay, h2 minus h2 is equal to h1 plus vf into p2 minus p1. P2 is going to be 3000, the boiler pressure, minus the condenser pressure, so that comes out to be 254.41. Now h3 is going to be obviously um, hf at 1000 kilopascals, because that is given that we have extracted the steam at 1000 kilopascals. Also, just know that um, this is an ideal uh, case, ideal regenerative Rankine. So the the steam coming out from the closed water heater, it's going to be saturated liquid. It's going to be saturated liquid. That is why the third state is where it is on the graph right here, and um, which can be calculated. The enthalpy of this point can be calculated by the table, which comes out to be 7. H4, the same formula. H4 is equals to S3 plus VF3 into P4 minus P3, comes out to be 765. Now we are going to apply heat balance in the closed feed water heaters to find the value of Y. Y is what we're looking for. That is the amount of heat extracted. So again, applying the heat balance. So H7 minus H3, I told you that the Y amount of steam is being taken from seventh state to third state in the closed feed water heater, and one minus Y amount of steam has been taken from the second state to the ninth state. So that gets you the value of y, which comes out to be 0.1957. So about 20% of steam they have already taken out for regeneration. Again, heat balance application in mixing chamber. So H5 is what you get um, as the enthalpy out of the mixing chamber, and H9 and H4 is the enthalpy of entry for both the mixes 1 minus y and y. So you get the value of H5, which comes out to be 763.23. Again, Qn is obviously going to be H6 minus H5. Just know that the point of entry for turbine is the fifth state. Sorry, the point of entry for the boiler is the fifth state, and the point of exit for the boiler is sixth state. So the amount of heat in Q in is going to be at 6 minus H5. At 6 minus H5. And that is why the amount of heat I've written as at 6 minus H5, it comes out to be 2352, very close to the answer given. 2350 is what is given there. And amount of work by the turbine, it's going to be at 6 minus H7, and this is 1 minus y into H7 minus H8, only because some amount of heat, some amount of steam was taken out. So there's only 1 minus y amount of heat, amount amount of steam in the system for the low pressure turbine. So amount of work by the low pressure turbine, this is low pressure turbine, and this is the amount of work by the high pressure turbine. So H7 and H8 is what the low pressure turbine gets to work between, and that gets you the amount of turbine work. And pump work is going to be y times H4 minus H3, 1 minus y times H2 minus H1. Yes, are only pumps are only working between these two states. Let me just show you. So this is where the pump is working between 1 and 2 and between 3 and 4. So that is why we have put up the pump work equal to H4 minus H3, H2 minus H1. Plus, you should know that during the fourth state and third state, there was only Y amount of steam. And from second state and first state, there was only 1 minus Y amount of steam. So that gets you the pump work. So these were three problems out of the five that we are about to complete. For now, I'm gonna end the thing here, and I'll continue with the last two problems in the next video. You have a good day. Bye bye.